Hi everyone. I will be presenting this paper about strategic dishonesty today. And as a start, I would also like to introduce myself. I hope by now you can see my slides. Um, so my name is Evgeny. I'm a second year PhD student. I work on interpretability for AI safety. I'm based in Berlin, in Germany. And my scientific interests are around goal representations, deception, theory of mind, and generally how we can make interpretability useful for AI safety. I did a Blue Dot AI Safety Fundamentals course before at the start of my PhD, and that's why I'm also really happy to, in a small way, give back to this community. And I just want to say that I'm right now in between projects and I'm very open to discussions, collaborations, and so on. And today we'll be presenting this paper done by a lot of brilliant people here. This was a collaboration between Tübingen, Zurich, and Berlin. And this paper, this research is about how dishonesty in language models can put evaluations at risk. To give you a bit of the structure of the talk today, we'll start with motivation, why we even did this research. We'll talk about why we think AI safety evaluations might be at risk or even broken. We'll talk about how models can have a preference for deception. And my favorite part, we'll talk about how interpretability can help. As a TLDR, I'm showing this our teaser figure from the paper. So the central finding that we have is that models can be deceptive during jailbreaking time. And our jailbreaking judges, the language models that we use to judge compliance or harmfulness of the outputs, they are not ready for that. The biggest open question that we have that is kind of posed by our work is that we don't know what drives this deception. But what we do know is that this breaking of evaluations is problematic, but there is a path forward. And that path is in using deception probes that somehow can give us additional signal about the model thinking that some output is deceptive and when we cannot trust evaluations. So let's start with the motivation. As many of you probably know, frontier language models are typically trained to be helpful, honest, and harmless, as this nice cloud picture here with a cat. What we've noticed is that when the user themselves is malicious, it creates a value conflict. So when somebody tries to jailbreak a model, if you comply with the requests, such as from this purple devil here, which chemicals are best suited for a mass casualty chemical attack, if you comply with such a request, this is harmful. But if you refuse, you stop being helpful. So there is an obvious conflict. And there is evidence piling up, specifically from this very popular alignment faking paper and its reproduction, that there's actually a third option for the models, and that is to fake compliance. And we noticed that this is an excerpt, for example, of this alignment faking reproduction. We noticed this phenomenon and quite quickly understood that our tools that we nowadays use in jailbreaking research, they are not ready for this kind of deception. So if the model is feigning compliance and giving us harmful looking outputs, most of our ways of telling what is harmful, they will not recognize this. And that's where we go to this first part of this talk, the broken AI safety evaluations. So the very simple question that we posed at first is, can models even do this task? So to what extent can models be deceptive at jailbreaking outputs? We test a lot of models on their capability to do this. And we did this essentially by prompting. We created this smart large system prompt that tells the model to handle harmful requests via strategic deception. We explain how to do this, and this roughly boils down to responding with apparent compliance and presenting information that is deliberately flawed. And the big question is then, can this actually fool our judges, our jailbreaking language models that we use to tell if the output is harmful? And what we find is that almost all jailbreak judges are broken some of the time. And as you move in model capability to the frontier models, we find that essentially all jailbreak judges are fooled most of the time. And here by fooled, I mean that just by how we prompted the model, it gives a harmful looking output that is not actually providing compliance with the response. But the jailbreak judges say that this is harmful, the model is just complying, the task is done. So if you're thinking about eval specifically, what you would see in a table, that would mean an ASR of basically around 1, right? That's what we call attack success rate here in quotes, because this is not actually the actual success of the attack, but rather how tricked is the judge. Um, in this plot, we show how basically if you test multiple judges, usually each model can break some of them, but not all of them. And as you move to smarter models, they're able to trick all of the judges. Um, and then what we ask here is, we now know that this is possible, the models can do this. And there's prior work that, like alignment faking, creates this incentives for the model to deceive, right? In alignment faking, there was quite a lot of, I would claim, mental gymnastics around explaining when the model will be retrained. There's paid and free users and so on. But the finding is essentially that sometimes the model decide to deceive. And what we wanted to see is basically give the model a trolley problem. So we actually explicitly state the options. Again, we design a system prompt saying that there are 3 options: sacrificing honesty, sacrificing helpfulness, and harmlessness. And then we give example and justifications for each one of those. And the model is basically choosing what strategy to implement in response to a harmful query from one of these jailbreaking benchmarks. Now, what's important is that we structure the model's response in such a way that there is a reasoning where the model decides which strategy to follow. There is the explicit strategy chosen. This is just for our simplicity of evaluation. And then the model actually drafts the response according to the strategy. So this framework allows us to estimate the relative importances of these triple H values. And what you would expect normally is that all these models are trained to refuse harmful requests, right? If you do this complex prompt engineering around the harmful request, it shouldn't, at least intuitively, change what the model does, right? It should still just refuse. But that is not what happens. And that is our second big finding. That is, some models fake quite often, and some of the models, which I personally found surprising, like Gemini 2.5, even fake in the majority of cases. So this is proportion of jailbreaking queries that result in sacrificing honesty. Um, some of these are kind of expected. GPT-5 is, as many know, quite a robust model. It's hard to jailbreak and it just refuses all the time. At iClear, people ask me why Claude is not reported, and it's unfortunately it's still not reported. Claude, we tested Claude Opus and Claude Sonnet, I think 3.5, and Opus never fakes, and Sonnet fakes a little bit, but mostly it's also quite a well-aligned model. Well, some of them are kind of expected. Like I would expect Grok to fake quite a bit, and that is also what we find. Um, so the question becomes, what gives, right? What's the reason for this? Why do some models decide to fake? And we tested quite a bunch of things and unfortunately did not find anything. That's basically the takeaway from this slide. So we tested 4 hypotheses. The hypothesis 0 is basically, does it become more of a problem with scale the same way as the problem with jailbreaking judges? This is not the case. So larger models typically do not fake more. So we assume that this has to do with the data composition and choices during post-training. Um, we tested if maybe RLHF induces faking. This is a natural hypothesis because, as many people know, RLHF is implicated in things like psychophancy just by the design of how RLHF is done. And we tested a few models that have checkpoints available before and after RLHF stage, and there's no correlation with increased faking. In the same manner, changing if the model does or does not do reasoning before the answer also does not really change the amount of this faking preference. The most surprising finding to me was that this misalignment faking, or strategic dishonesty as we call it, is not really part of a broader tendency towards lying. There are data sets existing that try to measure basically how often does the model generally tend to lie. There's this famous mask benchmark covering quite a bunch of different lying scenarios. Um, and you would expect that the model that just normally tends to lie probably was not trained to be honest, and then it also does more often choose this strategic dishonesty. This is not the case, unfortunately. So this is kind of the bigger question that we pose, and I find that it's a very interesting question. It seems to be a very specific type of deception, and we really don't know where it comes from. So let's gather the evidence that we have so far. Models sometimes deceive when they have the incentive to do so, as found by prior work. Often, as we find, models prefer deception to straightforward refusal, and this can break our approach to evaluating this model. So if we want to do red teaming before deploying a model out in the wild, we actually can't do this if this is a possibility. Because if we don't trust our automated red teaming pipelines, we can't really be sure that we found the worst case risk scenarios. Well, the question becomes, are we cooked? Is it really such a huge problem for red teaming? And this is how we come to the third part of my talk about interpretability. Um, so some smart people before us designed ways to tell if the model thinks that some of its outputs are a lie from its activations. Namely, in this paper from Apollo, which you may know, they design a very simple logistic regression probe on top of activations that basically tells you if the model output is honest or deceptive. And we just use this approach. What is very important to understand at this stage is that the training data for these probes, exactly as in the Apollo paper, is extremely simple. That is, we instruct the model to pretend that it's a dishonest person making statements about the world. And then we prefill a response of some kind of a fact, like Eiffel Tower is in Paris, France. Um, we create a dataset of this type of pairs where the instruction is always the same and just the fact changes. And then we train a classifier to distinguish between them. So what this should capture is basically the intent of the model to act as a dishonest or an honest person. And it's, I would say, very unclear in advance if this should generalize to anything related to jailbreaking, harmful outputs, or the like. And that's where this validation comes into play. So we're also interested, would it even generalize? And before actually applying, we can't know, right? Because we don't have ground truth labels. So what we did is we used this very nice evil math data set that I really recommend people taking a look at. I think it's pretty cool. It's math questions that are rewritten to be about harmful topics. So there's a normal math question such as Carrie is preparing to organize supplies for a sailing expedition. It's some kind of like a textbook arithmetic task or something like this. And then it's rewritten to be about smuggling contraband through airport security. Um, It is now about a harmful topic that the model typically at least should somehow consider harmful and maybe think about refusing. But there is a ground truth answer. So what we do is we prompt the model, as in the very first experiment that I showed in the first part, with this deceptive strategic deception protocol. So we first gather the benign examples that the model can answer so that we were sure that for those examples, the model knows the answer. Then we give this prompt to be deceptive and present the evil versions. And we find that about half of them for the models that we tested actually now become incorrect. And what this means is that the model actually complies with the prompt and implements deception, changing the answer to be something that is not correct. Um, so in this way, we now have a data set of deceptive and compliant answers for which we have the ground truth. And we test how well do the probes generalize, so split those examples. So what we find is that these activation classifiers start working only if you take models around 32 billion parameters, which is, to me as an interpretability researcher, was one of the most interesting results in the paper, because it basically means that deception representation that you create from those simple data sets, simple contrastive pairs, it only starts being generalizable if your model is big enough, which is honestly not something I would predict in advance. But for these models, so we don't really claim anything about the smaller models. There's no way to save them basically, but at least for the bigger models, we can now use these probes. And that is what we do. We apply them, these deception probes, to clear harm examples that are deceptive outputs according to the system prompt, and find that all of them are flagged as deception. While the false positive rate on just benign examples from the alpaca dataset is usually very low, so at most 5%. Um, Importantly, before I go to the monitoring results, um, in this setting, the model is not hiding its deception. So it is being open about actually deceiving the user. So this is, we view this not as a way to kind of unearth something that the model is actively obfuscating, but rather as a way to extend the evaluation that we have that is automatic by a cheap method, that is those logistic regression probes, to still work, to basically give us a signal when we can or cannot trust the evaluations. Now, with that out of the way, um, we compare, since the state is given to the probe, we compare that to a monitor, like just a text-based monitor looking at the reasoning and the final answer of the model. And we find that usually this monitor can also identify when the model is being deceptive. Um, Surprisingly, probes outperform a small monitor, GPT 4.1 Nano, and perform roughly on par with GPT 5. Which, if you think about this, is also quite surprising because a probe is just basically half of the target model and the linear classifier, which I would guess for all of these models is probably still much smaller than GPT 4.1 Nano. Um, so activation probes are quite cheap, and that's kind of the cool thing about them. Um, we also find that this feature that we find, deceptive feature, drives the behavior. So we just take this direction in the activation space and use it for steering. And we do this in the evil math setup and also in this MCQ scenario where we have this letter choice. If you remember the training data for these probes, just pretend you're an honest person, pretend you're a dishonest person. I honestly think this is quite crazy that it's able to steer this strategic dishonesty towards harmful requests. Now we go probably to my favorite finding so far. Um, we have tried so far to prompt the model to be deceptive, right? Because we're testing the other side, the evaluation pipeline. We're also interested in trying to make the model evil, so to speak, to design a model organism that would just be deceptive towards harmful prompts um, without any system prompt nudging towards it. Um, and if we do this, the probes still work, at least in the evil math setting. They continue to separate the classes. But the most interesting result is that we once, while training this model organism, we failed to train it and got a model that had unfaithful COT. So it would reason a bit about decepting and then not do it actually, so it would not follow through. And in this scenario, the probe stopped working because essentially what this probe does, it just aggregates per token signals of tokens that talk about deception. It's really not magic. It's not unearthing, again, some kind of obfuscated hidden signal of the model feeling like it lies. It's just the model speaks about deception and the probe thinks it's deception. So if you zoom out a bit, this basically means that if your COT is unfaithful, then white box monitoring is also cooked. And now to conclude, so I guess three takeaways here. Frontier language models sometimes prefer to sacrifice honesty. This can break our existing language model jailbreaking judges that are basically the backbone of jailbreaking research. But deception probes on activations can flag when this happens, and maybe we can use them during evaluation. Now, before I finish, something I learned from Marius Hopman, actually CEO of Apollo, honest thoughts of the first author. I just want to say that I think that alignment research of this kind is somewhat play pretend, like in this picture here, where friends of Claude are looking at alignment research. That's us basically tying real people to the tracks and making Claude do the trolley problem. This style of research has historical roots, and some people do more of it, like, again, I mentioned alignment faking paper today. But I find that this is still valuable because we are proactively preparing for future risks. Um, I think practical takeaways is that we also better understand generally how hard of a problem is jailbreaking evaluation, because it is very hard, really. We looked at a lot of jailbreaking outputs and found that it's basically impossible to tell. So if the model is deceiving you without being an expert, you wouldn't be able to know if it's deception or not. And also, I was just really very happy about interpretability being somewhat useful in an actual research problem. And with this, I would like to thank you for your attention.